Hello friends. In this session we are going to discuss about the application of network theorems to DC circuit with Norton's theorem. So this theorem states that any two terminals of a network can be replaced by an equivalent current source and an equivalent parallel resistance. The constant current is equal to the current which would flow in a short circuit placed across the terminals. The parallel resistance is the resistance of the network when viewed from these open circuited terminals after all voltage and current source have been removed and replaced by internal resistance. This is the representation of Norton's theorem. Norton's theorem in parallel with its resistance and then load resistance RL. Steps to be followed in Norton's theorem. Remove the load resistance RL and put a short circuit across the terminal. Find the short circuit current, that is ISC or Norton's current IN. Find the resistance Rn, called as Norton's resistance, seen from the point A and B. Replace the network by a current source in parallel with its resistance. Find the current through the load resistance by using current division rule. So some practice numericals. So find the equivalent network across the terminal A and B. So first step is the calculation of VTH. So mark the location of VTH in the network with its polarity. Then apply KVL to the mesh. Mesh 1, that is 2 minus 2 I1 plus 0.5 I1 minus 1 I1 is equal to 0. Then you will get the value of I1 as 0.8 ampere. Then write the VTH equation in the outer path, that is 1I1 minus VTH from path A to path B. Replace the value of I1. You will get the value of VTH. Now step 2, calculation of Norton's current IN. Now you short circuit the terminal A and B and mark the Norton's current IN. When a short circuit is placed across the 1 ohm resistor, it will get short circuited and hence current flowing through 1 ohm resistor I1 is 0. So the same network can be redrawn like this. The dependent source of 0.5 I1 depends on the controlled variable I1. When I1 is 0, the dependent source will get vanishes. Therefore, 0.5 I1 is 0 and hence the Norton's current IN is 1 ampere. Next step, calculation of Norton's resistance Rn. Rn is equal to Thevenin's voltage divided by Norton's current. Then step 4, Norton's equivalent network. So 1 ampere current and 0.8 ampere resistance, ampere 0.8 ohms resistor. This is the Norton's equivalent. Let's see the another example. Again, for this terminal A and B, for calculation of VTH, mark the location of VTH. Again, identify the mesh. Now in this case, I2 is equal to Ix and I1 is minus Ix. Now apply KVL to mesh, that is 5 minus 10 Ix minus 5 Ix minus 10 I2 equal to 0. Arrange the equation and get the value of Ix and I1. Now write the VTH equation. 5 minus 10 Ix plus 3 I1 minus VTH equal to 0. Substitute the value of Ix and I1. You will get the value of VTH. Next step is the calculation of Norton's current. Now you short circuit the terminal A and B and assume the current IY is flowing to the mesh 2. Accordingly, I2 is equal to Ix and I1 is Iy minus. Now again apply KVL to mesh 1. You will get equation 3. Then apply KVL to mesh 2. You will get equation 4. Solving this equation 3 and 4, you will get the value of Norton's current. Step 3 is the calculation of Norton's resistance, which is VTH by IN. Then last step is Norton's equivalent network. Numerical for practice. Thank you.